angle theta, right? We've got a block on top. It's going to slide down. All right. It's going to turn out that it doesn't make any difference what the mass is, but we shouldn't be surprised about that, right? And we'll call this height h. H is the vertical height above the ground. And for comparison purposes, let us suppose that we also have an object that's sort of suspended in air. We're holding it, if you will, and we're going to let it go, and it's going to fall straight down in a free fall fashion. It's going to fall a distance of h. So in both cases, we've got a height of h above the ground. In one case, we've got a free fall straight down. In the other case, something is sliding down an incline. Now, we want to look at what are the speeds when these two objects hit the ground, and maybe how long does it take before these objects hit the ground? What are the times required for these objects to hit the ground? Now, what would you think? Before we actually analyze this, what do you think is going to happen? We want to make sure that this stuff that we come up with makes sense to us. Well, if I let these two go at the same time, one sliding down the incline, one's falling straight down, which do you think is going to hit the ground first? You would think the one falling straight down, right? It hit the ground first. Okay. How fast are they going? So how fast, when this one reaches the incline, or the bottom of the incline, how fast is it going compared to how fast this one is going when it hits the ground? What do you think? Same speed, different speed. You think they'd be different speeds? Which one's faster? Well, let's look at that, okay? So what I'm going to do, we don't really need to do a free body diagram here. It's pretty straightforward. It's just a straight up kinematic problem here. But let's look at this one. Okay, so we've got a straight down vector. What's this vector?
mg.
And this is always mg. Mass times gravitational acceleration, that always goes straight down, right? Always goes straight down. Whatever the incline is, it's always straight down. But if it's inclined, we also have a normal, of course the normal force is going this way. That's always perpendicular to the surface that the object is resting on. And countering this, of course, is the vector going in this direction here. Here's my two component vectors. One going perpendicular to the plane, the other going parallel with the motion. This angle here is also theta. We've never really proven that, but effectively this angle is going to be this angle as well. So this vector is what? This little one that's going down the plane. That's, in terms of theta, what is that? Mg something. Okay, very good. So I'll just put a little thing there. So mg, I'm not going to have room there. Mg sine is opposite over hypotenuse. Okay. And so this one here that is perpendicular to the plane, of course, is going to be mg cosine theta. Okay. So what are the forces acting on this particular object? Well, we've got this one here, which is mg sine theta. Yeah. That's pulling the block down. Now, what's keeping the block from wanting to go down? Friction, and it acts which direction? Very opposite direction. Okay, so it's going, friction is going this way. We call that F of F, force of friction. Okay, so that's our free body diagram for the block sliding down the incline. Okay, so we'll call this the x direction. Okay. Forces in the x direction. Well, it's going to be the force of friction minus mg sine theta. Is this a first or second law problem? Second law. So in second law, this summation is equal to what? First law is equal to 0. It's equal to 0 means things not moving. It is moving, so it's equal to MA. Very good. And because it's going in the negative direction, it's actually minus. Sign straight here. So that's basically our Newton's second law equation for this particular scenario. Now I'm going to make this easier. We're going to say the force of friction is 0. Okay, make it easier. So the coefficient of static, coefficient of kinetic friction is equal to 0. Now, we already know that this is not true. Okay, but we're going to say that we've got a highly polished plane, and we oiled our object really good, so there's virtually no friction, so we're going to set that equal to 0. Well, if we do that, look what we have. So if I multiply through by negative 1, I get rid of the negative sign. Right, so mg sine theta is equal to ma. As we anticipated, the masses cancel, so that the acceleration is equal to gravitational acceleration times sine of theta. Now this is only true if there is no friction. If there is friction, then the expression is of course a little more complicated. It would depend upon the mass, because friction depends upon the mass. Okay? Usually the heavier it is, as we've already found out, the heavier it is, the more frictional force, the higher the frictional force. Okay. Now, we're going to look at this from a kinematic perspective. In other words, we want to know the time required maybe for the block to slide down the plane. We want to know its final speed when it gets down to the bottom of the plane, so that's looking at it from a kinematic perspective. So we're going to be interested in this distance here, because this block has to go from here all the way down to here. Slides all the way down to the bottom. So we need to know what that distance is. We'll call it R. Okay, the distance of the plane. Now R is not H. H is the vertical distance. R is not the horizontal distance either. Okay, R is that distance in that plane. Now question, what is the relationship between R, H, and theta? And sine, let's look at this. Sine of theta equals to what? H over R. H over R. Everybody okay with it? This is basic trigonometry at this point. Okay? So you see that the sine theta term occurs in the acceleration term, and also it occurs in the geometric term that describes our system. I'm interested in R, not so much H, because R is the distance that's covered. So what I'm going to do is I'm going to multiply both sides by R, so that's going to give me R sine theta equals H. Then I'm going to divide through by sine theta. That's what I want. The reason I do that gives me the expression for R. That's equal to H over sine theta. So what I've done is I've kind of set this up, looking at all the force terms and the geometric terms. Now let's introduce our kinematics. And specifically, here's one we want to look at. Final velocity squared is equal to the initial velocity squared plus 2 times the acceleration times the distance. All right. Can you see this? I'm sorry, I'm getting a little low back there. I apologize. You don't have to memorize this equation. I'll give it to you on the test if you got a problem. Is everybody okay with that? I haven't memorized. You do need to know what it means, and you do need to know how to use it, but you don't have to memorize it. Now, this is the final velocity, so that's this down here, V of F. This is V initial. Remember, I is initial, F is final. Okay? And everything is always final minus initial. Okay? That's the delta. 2 times the acceleration times the distance r. So whatever the acceleration is and that distance r, then that's going to give me my final speed. Now what's my initial speed?
0.
Yeah, I'm setting it on the top there. Now if I set it there and I pushed it, I gave it a little shove. Sometimes you have to do that because you set the block there, it's not, you have to push it a little bit to get it to go. We're going to assume that we don't, well, we won't have to do that because it's frictionless. Okay, but if you did do that, you give it some initial velocity, most likely you wouldn't know what that was. So you could introduce some systematic error in your analysis. Okay, we won't go there, okay? Let's just say it's 0. Make it easy. 0. So let's look at this. That means the final velocity squared then is equal to 2AR. Now, I don't want the square of the final velocity, I just want the final velocity, so what do I have to do?
Square root.
Just take the square root of both sides. If I do that, then that means my final velocity is equal to the square root of 2AR. Now, I'm running out of space here. I'll have to continue this. I guess I'll do it on this board over here. Now, I don't really want this in terms of A and R. I actually want this in terms of G and H. Because putting it in terms of G and H is going to allow me to compare it with my free fall object over here. And the one I'm just dropping straight in. Okay? Because here it's going to be H and it's going to be G. The free fall block is subject to gravitational acceleration. It's not being hindered by anything like this. This is here. This is being hindered by the plane I'm sitting on. It can't fall straight down because it's sitting on a plane. It has to slide down the plane. So, in order to compare apples, so to speak, I've got to change A to G and R to H. So let's do that. I'll do that over here. So, final velocity. This is of the block that's on the incline. Oh, I probably should. Here, we'll do this. So that's my final velocity for the block on the incline. I'll give it a subscript incline. Is that okay? Because I have to distinguish that from this block over here, which is not on the incline. Anyway, so that's equal to square root. Now what I want to do is I want to replace this acceleration, and let me show you this. You will agree? And then R replace it with that term. Because I don't want R in my equation and I don't want A, I want H and G. Because now I can compare with my free fall block. So, having said that, let's do that. So I got 2, and A is G sine theta. And then R is H over sine theta, H over sine theta. We'll agree. Does that look reasonable? You okay with that? Sort of, kind of. What cancels?
Sine theta.
Looks like sine theta cancels, doesn't it? Square root. So the speed of the block on the incline when it hits the ground, the bottom if you will, its speed is the square root of 2 times gravitational acceleration times the vertical height. Okay, now let's look at our free fall block. That's going to be equal to square root. Same equation, except A now is just G because it's free fall, and R is H because that's the vertical distance. So it's 2 square root of 2G So, what are the speeds of the two blocks? Are they the same or are they different?
They're the same.
What would be the same? So, the speed of the incline block is equal to the speed of the free fall block.
Can you show you how you got to the speed of the free fall block again?
What term are we looking at?
How did you get the square root of 2dh for the free fall?
Let me redo this. Same equation, but we don't have any initial speed on the free fall block, so that's equal to 0. A is equal to G, gravitational acceleration, because there's nothing hindering it. Let me say this is G. So basically, let me do it this way. It's that. Force vector on that free fall is in G. Okay, just like it is here, but the direction is straight down because there's nothing hindering it. So that means its acceleration, people agree, is G. It's falling a distance h, vertical, so v squared is 2gh. And of course it takes square root. Got it? Okay. Yeah, that's kind of an important point. Glad you brought that up. So they're both going at the same speed. However, they don't have the same velocity. Okay? We've got to keep our semantics straight. Why don't they have the same velocity? You can have the same speed and not have the same velocity. You go down the highway at 60 miles per hour, the other person going in the other direction is going 60 miles per hour, both of you going the same speed, do not have the same velocity because you go in different directions. I think I answered that question. You're going in different directions. One's going straight down, one's going at an angle. That makes the velocities different because velocity is dependent upon the direction as well as the magnitude, so they don't have the same velocity. And that, hey, by the way, that makes for a good test question. Do these have the same speed? Do these have the same velocity? Yes? No. Okay. So they have the same speed. Now, we didn't predict that. I think somebody predicted that this one would have a higher speed than this one over here. But according to our analysis, they have the same speed. Although they don't have the same velocity because the direction is different. Now, in reality, if you were to do this experiment, would you expect these to have the same speed? You've done enough experiments now. What do you find? What is always present when you do experiments and you can't get rid of it? Friction. Now, sometimes friction is our friend, sometimes not. Okay? But whatever the case may be, we have to take it into consideration in most cases. All right? When you do the analysis today with the Atwood experiment, we didn't account for friction. You're going to find out that friction ends up being an important term that you didn't account for. You go back and account for it, but it makes the analysis a little more complicated. My guess is you probably don't want to do that. That's fine. Okay, so these are going at the same speed. Now, question. Does it take the same amount of time? Is this one going to hit the bottom at the same time that this hits the ground? And how would we figure that out? Well, obviously we're going to use another kinematic expression, right? Because that's kind of what this problem is about. So let's look at that. Another space to work on. Let's just go back over here. The equation that we probably want to use is this one. Okay, so final velocity is equal to initial velocity plus acceleration times 10 to the 9, delta t. This equation is true as long as the acceleration is constant, which we assume kinematic expression. So again, our initial velocity is 0, so we'll set that equal to 0. Divide by a, right? A. So delta t is equal to the final speed, final velocity over the acceleration. Okay, that's your delta t. And we have a delta t for the incline That's equal to something, and then we have a delta t for the free fall. Blah. And that's equal to something. Now what is that equal to? Tell you what, I'll let you work on that for a couple minutes, see what you come up with. Now what are we anticipating? Are these two delta t's going to be the same? What do you think? What makes sense? You know what makes sense. Because nothing makes sense to us. It's all confusing. Yeah, it's all confusing right now, right? But no, seriously, what makes sense? Is this going to hit first or is this going to hit first?
The free fall?
You think the free fall. So we're anticipating, well, you are anyway, you're anticipating that delta t of incline is greater than delta t of free fall. That's what you're anticipating.
Yes.
Are you right? Work on that for a minute. Yeah. Oh, by the way, all you have to do is we got the acceleration, right? And we got the final speeds. Here are the final speeds divide each by the acceleration. One is a, one is g. Which one? See if those expressions are identical. We'll step out and I'll be right back. You have a square root of g here and g in the denominator. After all, g is g, right? Okay. All right. Looks like to me one's got a sign and the other one doesn't. Is everybody finding that? The delta t of incline has a sine term in it. And of course, the delta t for the free fall, I mean, it's going straight down. It's not going to have any trigonometric term in it. Right? I think most of you are getting this. So for the incline, that is, well, they're the same, aren't they? As far as the speeds are concerned, this is 2gh. But the acceleration for the incline block is g sine of theta. So it's g sine theta. Now let me do a little sidebar here. We've got a square root of g in the numerator and a g to the first power of the denominator. We can actually consolidate those terms and make this a simpler looking equation, and I'm going to do that. If you had something like 1 over 2 times the square root of 2, okay? This is a 2 and this is a 2, okay? So I can maybe combine those terms somehow. If you want to bring this inside the square root sign, what do we have to do to it? this is a algebra skill that you want to have. If I want to bring it inside the square root, what do I do to it? Don't I square it? 2 divided by 2 squared. So as soon as I bring this 2 underneath the square root sign, I've got to square it, because the square root of a square is just the number itself, right? So this is 2 to the first power, this is 2 to the second power, this is just equal to 2 square root of 1 over 2. Square root of 1/2. So that's how I would take that 2 into the square root sign. Well, I say all that to say this. I can bring this into the square root sign. If I do, it's going to be the denominator, and it's going to look like this. Square root of 2h over g, and then multiply that by 1 over sine theta. Okay. Now, these two terms, if you don't do this, I mean, this is correct the way it is. Okay. Technically you can keep it this way, but this makes it a little bit more succinct, fewer terms. Okay, for the free fall, this is just square root of 2gh. Now the gravitational acceleration g is just as it is. Using the same principles we did a moment ago. This is square root of 2h over g. So, are the two times the same? Yes or no? No, they are not. Just like was anticipated, just like we predicted, they are not. The inclined one is in fact greater than the free fall one. So, the prediction is correct. And the degree to which they are different depends upon the sign of the angles. It depends upon how steep that angle is. Okay. The ratio of these two, just for giggles, delta t incline, do this, incline, over delta t of free fall, this times 1 over sine theta divided by, again, for free fall, then it's just square root 2h over g. You can see that these square root terms cancel, and we are left with 1 over sine. So the ratio of the two times is just 1 over sine theta. Now, get some idea of what we're looking at, I don't know, a typical value of theta. Let's say we have an incline of 20 degrees. Seems like an reasonable incline. Not very steep, it's a little more shallow. Okay. Work through this. What is sine of 20 degrees, and then take the reciprocal 1 over that number. Let's see what this ratio is. By the way, if you're in radian mode, you'll have to convert that degrees to radians. Pi divided by 180. Put it in radian mode. Now this is a great problem. I love this problem. Then I have to ask the question, well, if you did have a frictional coefficient that was pretty off, how would you handle it? know what the answer is, I just didn't look at this number off the top of my head. Anybody have this answer? Anybody have it?
First side, 20 degrees.
Yeah, just sign it 20 degrees. 20 degrees. So delta T incline over delta T free fall is 1 over 0.34, and this is what? It's about 3, isn't it? 2 point what?
2.9.
About 2.9. So at 20 degrees, the free fall block is about fall 3 times, just about it, boom, 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 before the incline block hit the bottom. Okay? Intuitively, that should make sense, because it's going to take longer to slide down the incline. Number one, it's a longer distance, number one. Number two, the acceleration is less. It's quite a bit less. About 1/3 of what G is, so it's going to put it around 3.2 or something like that. Meters per second squared, so there's a significant difference there. Okay. Now, if we did add coefficient friction to there, so the friction is not zero, that would slow the block down even more. Its speed would be less when it hit the bottom. We're anticipating this, right? I think we're correct in this. The speed would be less when it hits the bottom, and it would take it even longer. Okay? The speed's less, takes longer. If the coefficient of friction and static friction was too high, the block wouldn't move at all. Just stick it on there. It's going to take forever to do that. It's not moving, it takes forever to do that. All this should sort of make sense to you. Certainly at this point when we've gone through the analysis. Any questions on this? Okay, one more quick thing. I think what I'm going to do, I'm going to show you, like I said, one more scenario. Should be pretty quick because it's just vertical movement. Maybe Wednesday we'll work a couple of the problems that I assigned, okay? A couple of those problems, and then maybe Friday we'll move on to the next chapter. Okay? Because we've been in this chapter for a pretty long time. All right. So, this particular problem may not have a lot of application. It's just kind of an interesting scenario. It might, if you were moving furniture, and you got an incline that you push something up into a truck, okay, might have an application here. This other one maybe has a little bit of application if you ever ride in elevators, okay? Elevator. Brought in scale. Everybody does it. Just an egg. You've got to take an elevator and you have a scale that measures in pounds or whatever. I'm going to bring this to the elevator, stick it down, I'll stand on it, and see what happens to the weight when the elevator goes up and down. Here you are. And there you are, standing on the scale. island or not, I don't know. Okay, let's look at, let me erase this. Let's look at the force vectors. For one, U, there's always a force vector associated with U because you weigh something. Okay? You have some mass and you're in the gravitational field. So you're doing this number, there's U. And your force vector is mg. You always have that with you. Unless you go out in space and there's no gravitational field, then you don't weigh anything. You weigh nothing. Obviously, there's a normal force acting on that scale. Now, when you get in the accelerator, elevator, I'm sorry. There's the door. You walk through the door. Go inside the elevator. So you push the button. Now you can go one or two directions. You go up or down, right? Let's suppose you go up. Okay. So now, when you first push the button on the doors have to close first, right? You push the button. When the elevator first starts to move, it's going to accelerate in one direction or the other. Because it's not moving, it's going to start moving, it has to accelerate. One way or the other. Okay. When the elevator reaches a constant speed, then you're reduced back to a Newton's first law scenario. While the elevator is accelerating, you're in a Newton's second law scenario. Does that sort of make sense? So when you're accelerating one way or the other, you're going to feel the net force of that acceleration. So we're going to say that we're going up. Okay. So you push the up button, you go into the next floor. So we're looking at the Y direction. Okay. Top is positive. So this is equal to the normal force that the scale feels. This is what the scale is feeling. By the way, it's also what you're going to feel. And then minus, that's your weight. Because gravity is always trying to pull you down, right? And that's equal to MA, and that's accelerating up, going up, and MA is positive. So your normal force then is equal to MA plus mg. I can factor out the m, a plus g. Now I can factor out the g too, mg, and that would be 1 plus a over g. The reason I do that is because, if you think about this mg is your normal weight. That's your weight if you're not going up and down. Okay? If you're not accelerating up and down, that's your weight. It's your weight right now. Okay? That's what you weigh. So basically what I'm doing is I've got a factor here, A over G, that either makes me heavier or lighter, as the case may be. Either heavier or lighter. If the elevator is accelerating up, then I'm going to feel heavier. If the elevator is accelerating down, then the acceleration is negative, then I'm going to feel lighter. That difference in weight will be registered by the scale. The scale will see that weight difference. And if you're standing and looking at the scale, push the up button, I don't know, let's say the thing's reading 150 pounds, okay? That's average weight here. I won't delve into that too much, but nonetheless, 150 pounds, you push it up, well, button, the 150 pounds is going to get higher, 160, 170, whatever, something like that. And then when the elevator reaches its terminal speed, it's going to go back to 150. So as long as it's going up at a constant speed, it's 150. If you push the down button, look at that accelerator, that scale, then as the elevator accelerates down, because A is now negative, the 150 drops, maybe 140, 135, something like that. When the elevator reaches its terminal speed going down, then the weight goes back to 150. So it goes up, back to 150, down, back to 150, depending upon whether you accelerate up or down. Once the accelerator reaches its terminal speed, that is a first law scenario, and the scale reads at 150, which is your normal weight. Any questions? All right. Well, let's call it a day. We'll see you this afternoon.
What problems did you assign to us for us to do?
They are, go to the Canvas files, and I've got a whole problem set there. Most of those problems have been picked from the end of the chapter. Okay? I'll say the end of the chapter in the fourth edition. Those are the problems. Let me know if you can't find those. They should